We're going to start off the year in physics by looking at motion in one dimension. So literally, things that move in a straight line. We'll build on that as we go, and we'll take a look at things that move in other shapes other than a perfectly straight line. But before we do that, I want to show you a couple things. And I want you to take a look at this next video and decide whether you think things are moving or not moving. Here you have a garage sitting there and a really handsome guy walking through. So the question is, was the garage moving in any meaningful way? Last year in chem, you probably talked about the fact that atoms are always moving. So the atoms in that garage were vibrating all over the place, but that's not what I'm talking about. And you could probably even talk about the fact that there's always some kind of seismic activity, and so the ground is slightly shaking. I'm not talking about that either. I want to know if you believe that the garage was moving in a straight line or whatever, in any significant way. And then, was Sterman moving in any meaningful way too? And if you said yes to either of those questions or no, how do you know? What is it in your brain? What are you processing that says this is moving, this is not moving? What is it that's going on behind the scenes that lets you know? Well, let's take a look at some physics concepts here. So motion requires that you change a position over some time interval. But what's a position? A position is a spot in a reference frame. Okay, so we're just going to take some frame and we're going to say, boom, here is where I am. That's my position. So what's a reference frame? Well, it's actually the way that you view what's going on. Okay, it's the way that you uniquely see the set of objects that you're trying to describe. Now, if you were in a math class, you'd be expected to say, well, this object is at this point in my coordinate system. So we would set up a set of x, y, and z axes, and then we'd say, okay, this point is at x comma y and or 1 comma 3, and we would all know what we were talking about. So reference frames are really important to every physics problem. It's probably going to be the thing that we talk about throughout the entire year, because how you view something is going to determine the math that you do, and it's going to determine the answer that you get. So I want to show you this video. It's pretty old. I'm pretty old, and this was made long before I was born. But this video is excellent. I want you to take a look at it, and we'll talk about it when it's done.
We are used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object, such as this ball, can be specified using these 3 reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the earth. And these 2 reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this earth frame of reference and in other frames of reference moving in different ways relative to the earth frame.
So a reference frame is more than just a way that we look at it. It's actually like influential on how we see everything. So I'll give you another example. Right now, I want you to point to the right. This is my right hand. I'm pointing to the right. Am I pointing in the same direction that you are? Why not? Like, what's going on there? Wouldn't we all agree on where the right is? Maybe not. The way that you view things, it often changes what you see. So in order to figure out a distance, like if something moved, we need to find out what the difference is between 2 positions. So in a math class, we would just say, well, you had an original x position, x1, and you moved to a new position, x2. So if we subtract those 2, then that would be the distance that you moved. We always in physics separate the end from the beginning, right? So it's always going to be the end minus the beginning, in this case, 2 minus 1. Will we agree about the position of an object? So where are you right now? Okay, if I asked you, give me a mathematical like coordinate system and place yourself in it, where are you? Are you at the origin? Are you at 1, 4? Are you at 27, 56? Where are you? And this should be painfully easy. Just look down, like underneath your feet. There should be a bunch of numbers painted, right? There are at my house. Okay, like this is new. This is like, how do we know where the origin is for a coordinate system? Well, you get to pick it. That is your reference frame. You get to say wherever you want is like that's where you're standing. So will we agree about the position of an object? Probably not. Like I believe that I am at the center of the universe. It's just how I am. So I'm going to place myself at the origin. Where'd you put yourself? Will we agree about the distance from one object to another? Like maybe we both think we are at the origin. So wouldn't we have a distance of 0 between us? Well, probably not, actually. If I measured the distance from my house to your house, and I say that that's 25 miles, if you measure the distance from your house to my house, you better get exactly the same answer. So it's weird. We will disagree about certain things in our reference frame, and we're going to agree about other things. So take Mrs. Crab here. I put her on a reference line. a number line, and, well, doesn't this number line need some numbers, right? So I'm going to say, look, Mrs. Crab is starting at 0. And I'm going to have Mrs. Crab walk to 3. So she's going to end up at 3. How far did Mrs. Crab go? Well, she actually has a distance of her ending position minus her beginning position. So 3 minus 0, she moved 3 units. But maybe you don't agree with my original reference frame. Maybe you're one of those people who believe that the 0 position should always be on the last tick mark of any number line. So wait, if that last one is 0, then that means Mrs. Crab actually started at -7 and then walked to -4. So she started at -7, walked to -4. So -4 minus -7 gives me 3 units. So we agree on the fact that Mrs. Crab walked 3 units, even though we describe where she walked from and where she walked to very differently. We can also do this with clock reading. So what do you think a clock reading is? It's just what the clock says at the instant that you look at it. So look at your clock right now. What's it say? Now, time interval. A time interval is like a distance, but only through time. A time interval is going to be the difference between 2 clock readings. So in physics, we will use the symbol triangle or delta as a shorthand way to say it is the difference between 2 things. So if I write triangle t, I mean delta t, and that's going to be the ending time minus the beginning time. So I've been blabbing on a lot again. Look at your clock. Does it have the same clock reading? No. So if you subtract those 2 clock readings, you will get the time interval that I have been talking. Will we agree about these things? So look at your clock right now. Now, whatever time you just saw, if you instantly called someone who was in China or India or Pakistan right now, would they agree with you on what time it was? Probably not. Like the middle of the night, could be a day earlier, right? So you will disagree about the clock reading, but if you said, look, I'm going to let 5 seconds pass in this phone call right now, and then I'm going to like snap my fingers, do you think the person on the other end of the line would agree that 5 seconds had passed? Probably, right? Because even though we may call this instant in time here by a different name, the difference between here and here, we're both going to describe as roughly 1 second. So let's go back. In the very beginning of this video, I showed you a garage and a really handsome guy, and I asked you, were they moving? Is the garage moving? How many people said no? Well, think back at the video that I showed you. Moving, you always have to ask, with respect to what? I have a camera filming the garage. Is the garage moving with respect to the camera? And the answer is no, right? Is the garage moving though? Sure it is. It's anchored to the earth, and the earth is spinning around an axis once a day, and the earth is going around the sun once a year. If you total those up, we move about 4 football fields a second. So that garage is actually flying through space faster than you can imagine. So why does it look like it's just sitting there? Because everything in our reference frame, the reference frame that we normally use, is also moving at that same incredible speed. And so we don't even think about it. It's just normal. Well, what about Sterman? Was Sterman moving? No. Nope. Actually, what I was doing, I was staying in one spot and I was pushing the entire earth under my feet, right? So that the camera, the garage, the trees behind it, the entire earth was shifting underneath me. Is that insane? Probably. But from a physics point of view, is it wrong? Maybe not. Because in my reference frame, whether you say that I am moving to the right, or I say that actually everything else on the earth was moving to the left toward me, mathematically that is exactly the same. Okay, so when you get asked questions, two people may give completely different answers that are both 100% correct. And so we need to nail down what is our reference frame whenever we answer that. So the things I need to take away today, I need you to know that reference frames are going to influence everything that we think about. I need you to know what a position is and how that is different from a distance. I need you to know what a clock reading is and how that is different from a time interval. In the next video, we're going to talk about how we measure movement, how we look at speeds, and then we're going to introduce some things like what's the difference between speed and velocity. All right, thanks.